Today I want to take you through a small exercise in denotational design, a way of designing software developed by Connell Elliott. A full treatment of it is outside the scope of this video and, frankly, my ability since I'm still learning its intricacies. The core of the idea is to derive implementations from a denotational specification, which is a specification expressed using well-understood mathematical structures. Accordingly, in denotational design, the first choice to make is that of the denotation, a mathematical structure with simple, precise, and well-understood properties. The simplicity of the denotation is very important. Without simplicity, we have little chance of understanding its suitability as a model of what we want to implement. A desire for simplicity is a recognition of our limitations as reasoning beings. Even the best of us are not particularly rigorous, accept fuzziness and contradictions in our thinking, and have relatively little patience. For us to say our implementation is correct, we must have something against which to measure that correctness. That something is the denotation. If it is not simple, our derivations and proofs will be correspondingly not simple. Worse, it may be hard to discern whether a complex denotation is a suitable model for what we wish to implement. Today we will look at a simple example of denotational design in action. As our denotation, we will consider the affine functions. You may recall from high school algebra that such functions have the form f of x equals ax plus b for some constants a and b. In this exercise, our domain and codomain are rational numbers. Reasoning with the real numbers is surprisingly difficult and not currently supported by the AGDA standard library. While the denotation is the affine functions themselves, we want to come up with a representation of these functions as data. In this particular example, we have chosen pairs of rationals as our representation. Choosing a good representation is a key creative act in denotational design. In this example, the choices are limited and happen to be obvious, but this is not always the case. Once we have chosen the representation, we can, and should, define a meaning function that maps from the data type we have chosen to the denotation. In our case, the meaning function is defined as follows. The type of the meaning function is from pairs of rational numbers to functions from rationals to rationals. The definition says that given a pair of rationals a and b, it maps to the function f of x equals ax plus b. This function is expressed in AGDA by the lambda expression lambda x a times x plus b. Another question is, what should the API on this representation look like? Should we just choose an interface using our taste and experience? While this is the most common choice, perhaps there is a better way. Another key idea in denotational design is that the denotation can and should inform our design of the representation's interface. A good denotation should be a well-understood mathematical structure, replete with elegant and useful mathematical properties. The structure will often have operations that can be performed upon its components, that can then be transferred to the representation with little or no modification. Guidance from the denotation is far preferable to choosing an interface for the representation based merely on taste or experience, since many mathematical structures have had the benefit of decades, even centuries, of study and refinement. Affine functions are instances of a mathematical structure that has great versatility and applicability, known as the monoid. A monoid is a set combined with a binary associative operator. The set must contain a distinguished element that is both the right and left identity of the associative operator. A monoid is expressed mathematically as follows. In fact, affine functions are monoids in at least two ways. The first way that they are a monoid is under function addition and the constant function that returns 0. The addition of functions f and g is defined pointwise. That is, f function addition g is a new function, which at point x has value f of x plus g of x. The second way that they are an instance of a monoid is under function composition and the identity function. Function composition is defined as f composed g equals lambda x f of g of x, while identity is just lambda x x. Now we come to a key point that is much more powerful than it first appears. For a given mathematical structure, if we define analogous structures on the representation, and also stipulate that there is a homomorphism via the meaning function between the analogous structures and the denotation structures, then we get two things. One, we can use the homomorphism properties to derive the implementation of the analogous structures on the representation. That will be the main focus of this series of videos. Two, the laws that hold in the denotation are transferred to the representation for free. There is no need to do any further proof. In this video, I won't go into why the second point is true, but it is a key tenet of denotational design, and it allows us to treat the representation as if it were the denotation. The same mathematical properties hold, which allows us to use our understanding of the denotation whenever we use the representation. Doing so can be of immense utility when writing our programs. Now let's summarize what we're going to do in this series of videos. The API that we will define for our representation, pairs of rational numbers, will precisely mirror the mathematical structures that are defined on the denotation, functions from rational numbers to rational numbers. We will assume that the representation is a monoid, and then proceed to derive the operations for the two monoid instances I spoke of earlier. One monoid under function addition and the constant zero function, the other monoid under function composition and the identity function. One thing I'm really hoping to impart in this presentation is just how good AGDA is as an aid to denotational design. Its dependent type system allows us to do things that are qualitatively different from what is possible in other languages. I'll present a technique for deriving implementations from specifications that is not only intuitive and familiar to those who have done equational reasoning, but it's machine-checked as well. After all, there is no higher standard than a machine-checked proof. With that rather long introduction now out of the way, let's proceed to our first derivation. We'll consider the fact that the denotation is a monoid under function addition and the constant zero function, and, as our very first exercise, derive the corresponding addition function on the representation, pairs of rational numbers. See you in the next video.